We've all learned in our textbooks that energy cannot be created or destroyed, right? But what if I told you that's not entirely true? Imagine you're an astronaut floating alone in deep space. There's no gravity, no friction, no air. You pull a gun from your pocket and fire it into space. According to Newton's first law, that bullet should keep going straight forever, without anything stopping it. There's no outside force acting on it, so its motion should continue. Simple physics, right? But when scientists apply this thought experiment to the real universe, the result is completely different. The bullet fired from the gun travels through space, but after some time, it slowly starts to slow down. And eventually it almost stops without any external force. This means both Einstein's and Newton's theories fail here. But the question is, how? Where did the bullet's energy disappear to? Now, Einstein didn't want to admit this biggest problem with his theory. But then came a young scientist who not only made Einstein realize his mistake, but also filled this hole in the theory of relativity. She gave us a revolutionary theory that laid the foundation of today's entire modern world and answered the paradox that even Einstein couldn't solve. How photons lose 99% of their energy while traveling through space for billions of years, and where that energy goes. So hello guys, I'm Kaushik, and let's start another new episode. Now friends, before we go further in the video, just as you're connected with me on YouTube, I'd like you to connect with me on Instagram too. This is my Instagram user handle. You'll find the link in the description box. Go and follow me. So in 1915, Einstein was working on his general theory of relativity. This theory stated that gravity isn't an invisible force, but rather the curvature of space and time. Just like a heavy ball presses down on the surface of a trampoline, planets and stars create a curve in space-time, through which other bodies move. Now, Einstein's lectures were happening at Göttingen University, and the entire academic world was fascinated by what he was saying. But there was one thing that was bothering Einstein internally. He couldn't find the balance of total energy anywhere in his new equations. A basic rule of physics is that energy is never destroyed. If there's some motion in a system, some particles interacting, their combined energy should remain constant. But Einstein's new gravity equations didn't show this conservation. He was confused. Is the energy hidden in the curve of space-time, or within matter? Or is it a combination of both? His doubt grew. Now, another brilliant mind who listened to Einstein's lectures was David Hilbert. He was a legend in mathematics. Impressed by Einstein's theory, Hilbert started analyzing the equations himself. He discovered some mathematical identities called Bianchi identities. These identities mathematically proved that energy could be conserved, but only in an empty, perfectly empty universe. Meaning, where there are no stars, planets, atoms, nothing at all, just an empty vacuum. But our universe is full of galaxies, black holes, stars, and dark matter. So this solution was practically useless. Hilbert gave up. But Einstein still didn't give up. He proposed a new idea. The energy of matter and the energy of the gravitational field should be added together to create a total, and that total should be considered constant. He created an equation where energy seemed conserved, but that equation had a problematic mathematical object called a pseudotensor is something that changes its value when the coordinate system changes. This means if you're an observer on Earth and another is in the moon's orbit, both would see a different value for the same energy. In other words, the existence of energy also depends on the observer's frame. This was completely against the basic rule of general relativity, general covariance. He was breaking rules just to save energy conservation. Seeing all this, physicists and mathematicians were confused. On one hand, the theory's structure was majestic. Curved spacetime, geodesics, tensors, everything was precise. But there was no stable explanation for something as fundamental as energy. Einstein was constantly modifying his equations, but the solution still wasn't fitting correctly. His theory was stuck at a certain point, and at this moment, an individual entered the stage of science whose name no one had heard of at the time. She wasn't a professor, she didn't have a salary, nor was she officially admitted to the university. And her name was Emmy Noether. She not only filled this hole in Einstein's theory of relativity, but also gave a theory that revealed the secret pattern of how the universe works to humans. It was called symmetry. This single word contains all our knowledge of physics, the universe, and the quantum world. But how? Let's understand it. So, in 1915 Europe, a young woman was quietly writing equations on a blackboard with chalk. No press conferences, no awards, no applause, just a mind silently breaking down the most complex theoretical problems of that time. This was Emmy Noether, a name that still hasn't received the recognition it deserves in science textbooks. But the work she did, our entire knowledge of physics and the universe today rests upon it. Now, Noether studied at Erlangen University in Germany, but not as a student, rather as an observer. She was allowed to come to the university, but she wasn't officially admitted because she was a woman. But this discrimination didn't break Noether. Instead, it motivated her to work harder. Quietly, she learned everything, even better than her professors, and even the top mathematicians and scientists in the field. Noether began to understand that if an object or function is changed in such a way that its identity doesn't change, then it's a symmetry. Whether it's reflecting a triangle in a mirror or shifting a graph slightly, if its nature remains the same, it falls under symmetry. This idea seemed simple, but its consequences became revolutionary for physics. Noether saw that all of physics' conservation laws, like energy, momentum, and angular momentum, are the result of these symmetries. And that observation gave birth to Noether's first theorem, a mathematically proven rule that states every continuous symmetry has a conservation law. Now, let's understand this with an example. What is symmetry, and how does it work? So symmetry means that the system's rules remain constant despite some changes. For example, if you do an experiment in Delhi and the same experiment in Mumbai and the results are the same in both places, that's called space translation symmetry. If something behaves the same way after rotating clockwise or counterclockwise, that's rotational symmetry. But the most important symmetry was time symmetry. This means whether you do an experiment today or tomorrow or 10 years from now, the laws of physics keep the results of that experiment the same. Simply put, Noether's first theorem says that if the rules of physics don't change with time, meaning today, yesterday, 100 years ago, or 100 years in the future, the laws of physics are the same as they are today, then there is symmetry in time. In this condition, energy will be conserved. This means that if a bullet is fired under this condition, it will follow Einstein's and Newton's laws and will always travel through space at the same speed and force until an external force stops it. But is the universe really like that? Well, no, because we've only seen half of Noether's solution so far, which, like Einstein's theory of relativity, had a hole. But the complete answer to Einstein's and our questions comes from Noether's second theorem, which acts as a conclusion to the first theory. So, when we observe light coming from the distant universe, whether it's the microwave background radiation coming from the edge of the universe, or the radiation from accretion disks of stars and black holes millions or billions of light years away, we see a special pattern in all of them. All these photons, after traveling millions, billions, or even trillions of light years through space, have lost almost 99.9% of their energy by the time they are observed by our telescopes. This means that photons that were born billions of light years away with high energy in the ultraviolet wavelength, even without any collision, have lost 99% of their energy just by traveling through the universe and have changed into radio waves or microwaves. In other words, 99.9% of its energy disappears. And where does that energy go? Well, traditional physics didn't have an answer to this question. According to classical physics, energy is conserved. It can be transferred from one place to another, but it cannot vanish or disappear. But when physicists started seriously looking at the expanding universe, they understood an uncomfortable truth. When time symmetry breaks, energy can't be saved either. Look, the universe isn't static. It's changing every second, every minute. Galaxies are moving away, space is constantly stretching, and this expansion never stops. Now, when we do experiments on small time scales like in a laboratory, the laws will appear the same. If you do it today or tomorrow, the result will be the same. But when the timescale becomes millions or billions of years, symmetry starts to break. And where there is no symmetry, Noether's first theorem fails. In that condition, energy is no longer conserved. This was the point where Noether developed her second theorem, a concept where, instead of a conservation law, there's a continuity equation. The first theorem was for static and symmetrical systems, meaning a universe that is still, where there's no external force, and the universe itself isn't moving. But Noether's second theorem was for systems that are dynamic, meaning a universe where space-time constantly evolves. In such a universe, the law of energy conservation will also evolve, it will change, and it will break. Because over large time frames, as the space-time curve increases when gravity bends space, or when the universe expands, small cracks appear in space-time, through which energy starts to leak. That energy isn't going into another dimension or turning into dark matter. Instead, it's being absorbed into the curvature of space-time itself. Simply, Noether's second law, which applies to our evolving expanding universe, states that the break in time symmetry, due to the continuous evolution of the universe and the expansion of space-time at a universal scale, also breaks energy conservation. And in such a universe, over large timescales or large regions, the law of energy conservation does not apply. In short, Noether's second theorem showed that a local sense of energy remains, meaning you can still write equations in small regions. But globally, there's no perfect definition of energy. When you calculate by considering the entire universe as a single unit, you see that some energy is missing here. And this energy loss doesn't break any rule. Rather, it's a natural result of the breaking of symmetry due to the evolution of the universe and space-time expansion. This is why when we look at the cosmic microwave background radiation, which is considered the oldest light in the universe, its energy is almost gone due to redshifting. So, with these two theorems, Noether proved that time symmetry means energy is never created or destroyed. It only transforms. Noether's solution was so solid that when David Hilbert read it, he couldn't believe that Noether had found the solution to a problem that even Einstein, considered one of the most genius people in the world, was initially confused about. And she didn't just find a solution. She also explained that if you break the rules of symmetry, you can't keep the conservation laws stable either. Noether gave physics a new dictionary where every rule had a hidden pattern, and that pattern could be decoded through symmetry. Now, Noether's theorem wasn't just for classical systems. It also transformed future quantum mechanics, field theories, and even particle physics. When physicists observed the behavior of electrons in the quantum world, they found that electrons have a hidden phase, an invisible direction that can be rotated. Now, if you shift the phase of all electrons at once, their behavior doesn't change. Another symmetry. And that symmetry meant electric charge is conserved. Thanks to Noether's theorems, scientists understood for the first time that the existence of fundamental particles is also linked to symmetry. Later, this framework gave birth to the Standard Model, which defined quarks, leptons, bosons, everything based on symmetry. Even the Higgs boson particle, called the God particle, was predicted from this theory's framework. And this was Noether's greatest contribution. She showed that in some parts of the universe laws can change, and yet physics remains valid. If there's symmetry, you'll find conservation. If symmetry is breaking, energy can also leak. And this isn't a mistake, but the core design of nature. Now, if I were to conclude this entire video, Einstein's theory of relativity, which was breaking energy conservation, wasn't wrong. In a true sense, that theory was absolutely correct because it was giving results according to our space-time curvature and expanding universe, where energy is not conserved on a universal scale. This means that when a bullet is fired, it will eventually lose all its energy and stop, whether an external force stops it or not. But this was Einstein's mistake because he trusted Newton's law, which was made for a static universe, more than his own theory. A universe where there is no movement, or if there is, it's very little. And Newton's laws were proving correct before the 19th century because they were applied in a very small local region, like Earth or our solar system, where the overall evolution or expansion of the universe doesn't have much effect. And that's why Emmy Noether, with her first theorem, explained to Einstein and the world that if time symmetry is maintained, which will happen in small regions or any local system and in a universe without any motion, then energy conservation will be maintained there. Whereas for our real evolving dynamic universe, Emmy Noether, by giving her second theorem, explained that with the expansion of the universe and space-time, the symmetry of time also breaks, due to which the law of conservation is also not valid there. In short, because Einstein's theory of relativity was based on our real evolving universe, energy was not conserved. But because Einstein didn't know about the secret patterns of the universe, meaning time symmetry equals energy conservation, even after giving the world's most revolutionary theory, he was confused and doubtful about his own theory. Now, you should definitely learn one lesson from this video. No matter how much of a genius you are, or how much of a genius the other person is, they can also make small mistakes that they can never solve.